Howdy guys, today we'll be talking about sorting algorithms. The three main ones we will be discussing is bubble sort, insertion sort, and selection sort. And we will also end this discussion by talking about the lower bound theorem. So let's start with bubble sort. In bubble sort, the worst and average case are both O of n squared, while the best case is O of n. In bubble sort, the interaction consists that you are comparing the element with the element above it. And if it's smaller or if it's out of place, you just keep swapping. And you swap it one after another. And you go through this until there are no swaps performed on the entire loop. So let me quickly show you an example of this. As you can see in the bubble sort animation, you are comparing the two items side by side. If the algorithm finds that they are out of sort, it will swap it. Now notice how the biggest number always seems to find its way to the end. So in the first iteration, 8 makes its way all the way to the end. In the second iteration of this example, 7 will make it all the way to the end. In the third, 6, and so on and so forth. So the algorithm is actually sorting it starting from the end. From the right side, that's when it's going to be sorted. Let's move on to insertion sort. So again, in insertion sort, the worst and average case is O of n squared, while the best case is O of n. This is similar, or the same, as bubble sort. Now here, we're going to determine the correct index for each element in comparison to the elements before it. I'd like to consider insertion sort kind of like how you would sort a bookshelf. So imagine a bookshelf, you're trying to sort from smallest to largest. So what you're going to do, you're going to take that first book and you're going to take it as reference. So you're going to leave it alone. Next, you're going to take the second book. And let's say the second book is smaller than the first book. So you're going to take that and you're going to shift that first sorted part all the way back. And then you're going to put in that book in its right place. Now let's say that the third book is actually in between the first and the second book. So it's a middle size. You're still going to take that book, you're going to shift all the way down in order to make a little position, a little craning for that second book, and you're going to put that book in. So that's, in the end, how you end up sorting. Slowly but surely, just by inserting the items. Now, a key thing to notice about insertion sort is that insertion sort, although the beginning array is always being sorted more and more, so first the index 0 will be sorted, then index 0 through 1, then index 0 through 2, then 3, then 4, then 5. Notice that they're not in their final positions. So even though index 0 is from 0 to 4 is sorted, that doesn't mean that another number can come in and shift them around. Their index position is not permanent. They can still be shifted around even though the beginning is sorted. Next, we have selection sort. Selection sort is by far the worst one, as you can see that the worst, average, and best case are all O of n squared. How selection sort works is that it's actually going to select the smallest item and then going to put it at its correct index position. So notice here in this animation, 0 was found first to be the minimum, so it was put in index 0. Next, it looked for the next minimum and it found 1. And so on and so forth. Notice how once a place is sorted, once that area is sorted, a number is not going to be shifted from its index. This is different from insertion sort. So that 0 is there to stay at index 0 forever for the rest of the algorithm. It's not going to be shifted around. That 2, once it's sorted, is going to stay at index 3. Another key thing to notice is that each time it has to find the minimum. But to find the minimum, it has to look through the entire unsorted array. Even if I found the minimum in the first iteration, it still has to look through the entire rest of the unsorted array to make sure that it is in fact the minimum. So selection sort, again, is by far the worst. Okay, let's do some practice with iterations. Here you have to choose between whether this represents a bubble, insertion, or selection sort. And this will be on your test, so make sure you're good at these. So let's take this first example. So first thing we're going to do is going to look at the end. Because if the end is being sorted, that's a dead giveaway that it's bubble sort. But notice, okay, 7, 9. Okay, the 9 does not come at the end of the second iteration. So we know that can't be it. It can't be bubble. Next, we're going to look at the front. Okay, how's it being sorted? So you're going to look at this first, kind of like make a little triangle in your head. And what we're going to do is we're going to notice that once a number is placed, it is not moved at any point in time. So this 2 is here to stay. Notice how it's just one line. This 4, once it's sorted, here to stay. This 5, here to stay, so on and so forth. So we do see kind of this like triangle kind of form. And so because of this, we know that this has to be selection sort. Next, we're going to come here. And again, we're going to start at the end. Okay, 9. Okay, that's being sorted. Okay, 8, 9, 7, 8, 9. We notice it's being sorted from the back. Boom, we know it's bubble sort. Finally, let's look at the last one. Okay, is it being sorted from the back? 2, 2, no. We know that this is not being sorted from the back. Okay, next we're going to look is this like kind of, we make a triangle of like the sorted array. And we notice, okay, so here, this 1, okay, this stays consistent. Okay, let's see this 4, because this is the next like sorted part. Notice how like this line, it changes. It goes from 4 to 3 to 2. But it's still being sorted in its respective. So 1 to 4 is sorted. 1 through 4 is technically sorted. 1 3 4 9 is sorted. 1 3 4 7 9 is sorted. But because of this, that it's like kind of switching indexes, things are being shifted around, we know that this has to be insertion sort. Okay, now let's talk about the lower bound theorem. What is the lower bound theorem? So the lower bound theorem states that the best big O for comparing sorting algorithm is O(n) log n. Now notice, the best case can still be better. Notice how in bubble and insertion sort, we have a best case of O of n. This is better than n log n. But for the worst case cannot be better than n log of n. Take some time to absorb that, because this is important. So again, we can see that with bubble, insertion, and selection sort, the worst case was O of n squared. And we're not going to worry about the proof a lot. Just know that this theorem exists. Keywords here: comparison based and worst case cannot be better than n log n. Notice, we can achieve a better big O, but only with non-comparison sorting algorithms. And we can achieve a big O of n. But we have to make some assumptions on the data being ordered. That's either it being ordered in some kind of way, or that they're evenly distributed. Like there is some assumption that is being made on the data. Here are some few examples. There's counting sort, there's radix sort, and bucket sort.